Hidden beneath the serene landscape of eastern California, a giant sleeps. This isn't a creature of myth or legend, but a geological titan of immense power, the Long Valley Caldera. To the unsuspecting eye, it's a vast depression home to ski resorts, hot springs, and a town of mammoth lakes. But to geologists, it tests one of the most closely monitored volcanic systems on Earth, a restless supervolcano with a violent past and an uncertain future. Our story begins not with a whisper, but with a cataclysmic roar that echoed across a continent. 767,000 years ago, this tranquil valley was the site of one of the largest volcanic eruptions in North America's history. Deep beneath the ground, a massive chamber of magma had been growing for millennia, swelling and straining the crust above. When the breaking point was finally reached, the ground tore open. A colossal column of ash, gas, and molten rock rocketed miles into the sky, blotting out the sun. The eruption was so powerful it dwarfed the 1980 Mount St. Helens event by over 2,000 times. As the eruption column collapsed under its own immense weight, it unleashed pyroclastic flows, scorching avalanches of gas and volcanic debris traveling at hundreds of miles per hour. These flows incinerated everything in their path, burying the surrounding landscape under hundreds of feet of hot ash and pumice. This deposit, known as the Bishop Tuff, still covers an area of over 800 square miles today, a stark testament to the eruption's scale. The ash clouds spread far and wide, blanketing much of the western United States. Layers of this ancient ash have been found as far away as Nebraska and Kansas. The sheer volume of magma ejected was so vast, over 150 cubic miles, that the ground above the emptied chamber collapsed, creating the 20-mile-long, 11-mile-wide depression we now call the Long Valley Caldera. For thousands of years after this apocalyptic event, the giant slumbered and the world forgot the fury that lay just beneath the surface. For decades, geologists considered Long Valley a dormant system, a relic of a distant, violent past. The residents of Mammoth Lakes lived their lives in blissful ignorance of the power beneath their feet. But in 1978, the sleeping giant began to stir. It started subtly with a magnitude 5.4 earthquake deep beneath the caldera floor. Then, in May of 1980, just a week after the dramatic eruption of Mount St. Helens, Long Valley truly woke up. A swarm of powerful earthquakes shook the region. 4 separate quakes registered a magnitude 6 or greater, causing damage in the town of Mammoth Lakes and triggering landslides. The ground itself began to change. Scientists from the U.S. Geological Survey rushed to the scene. What they discovered was alarming. The central part of the caldera floor, an area known as the Resurgent Dome, was swelling upwards at a dramatic rate. This wasn't just tectonic shifting. This was the signature of magma on the move. Molten rock was once again accumulating in the chamber deep below, pushing the ground up like a slowly inflating balloon. By the early 1980s, the center of the caldera had risen by nearly a foot. The earthquake swarms continued, rattling nerves and reminding everyone of the active system below. In 1982, the USGS issued a Notice of Potential Volcanic Hazard, the lowest level alert, acknowledging the undeniable signs of volcanic unrest. The public announcement created panic and economic turmoil in the tourist-dependent town. The awakening of Long Valley was no longer just a scientific curiosity. It was a real and present threat. Throughout the 1980s and 90s, the caldera continued its restless behavior. The ground continued to swell, rising a total of over 2.5 feet since the late 1970s. Earthquake swarms became a regular feature of life in the eastern Sierra. Then, a new, more visible symptom appeared. Trees on the flank of Mammoth Mountain, a volcano on the caldera's rim, began to die off in large patches. At first, people suspected drought or disease. But the truth was far more insidious. Magma rising beneath the mountain was releasing immense quantities of carbon dioxide gas. This colorless, odorless gas, heavier than air, was seeping up through the soil, pooling in low-lying areas and suffocating the trees from their roots up. Areas like Horseshoe Lake became known as tree kill zones, eerie, barren landscapes fenced off to the public due to the lethal concentrations of gas in the soil. The death of the forests was a chilling, tangible sign that the volcanic system was very much alive and breathing. So, what does the future hold for Long Valley? Is another super eruption imminent? The short answer from scientists is probably not. While the system is undeniably active, The current level of unrest doesn't point towards an imminent cataclysm on the scale of the one that formed the caldera. The magma chamber is being refilled, but it's a slow process. What is more likely and still presents a significant hazard is a smaller eruption. This could take the form of an explosive blast from the Mono-Inyo craters, a chain of younger volcanoes that cuts across the caldera, or a less violent lava flow from the caldera floor itself. Such an event would still be devastating for the region, impacting infrastructure, tourism, and air quality. Because of this ongoing threat, the Long Valley Caldera is one of the most intensely monitored volcanic areas on the planet. The California Volcano Observatory, a branch of the USGS, maintains a dense network of scientific instruments across the region. GPS stations track ground deformation to the millimeter, measuring the swelling and sinking of the land. Seismometers listen constantly for the faintest tremors that signal moving rock or magma. Gas sensors monitor CO2 emissions, and hydrologists test the temperature and chemical composition of hot springs and fumaroles. This constant surveillance provides a real-time health check of the volcano. The goal is to detect any significant changes, like a rapid increase in ground swelling or a change in gas composition, that might signal an impending eruption, giving authorities crucial time to issue warnings and evacuate the population. Living on top of a restless supervolcano is a strange reality. For the residents of Mammoth Lakes, the dramatic geology is both a blessing and a curse. It creates the stunning mountain scenery, the world-class skiing, and the soothing hot springs that drive the local economy. But it also carries an undercurrent of risk, a knowledge that the very ground they live on is dynamic and potentially dangerous. The community has learned to coexist with the volcano. Emergency preparedness plans are in place, and public education helps residents understand the science and the risks. The relationship is one of respect and vigilance. Long Valley Caldera serves as a powerful reminder that our planet is not a static rock, but a living, breathing entity. The forces that shaped our world are still at work, often silently, but sometimes with a restlessness that demands our attention. The sleeping giant of California may not wake fully in our lifetime, but it continues to stir, reminding us of the immense power that lies just beneath our feet. Thank you for joining us on this journey into the heart of a supervolcano. If you found this story fascinating, please like this video and subscribe to our channel for more deep dives into the wonders and dangers of our incredible planet. Stay curious and stay safe. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. Imagine a giant sleeping beneath the sunny slopes of California, not far from Yosemite. This isn't a mythical beast, but something far more real and powerful. The Long Valley Caldera. For most of its 760,000-year history since its last colossal eruption, it's been quiet. But in the late 1970s, deep beneath the surface, something began to stir. Molten rock, a massive body of magma, started to awaken from its long slumber. It began to push upwards, pressing against the roof of its subterranean chamber. This was the silent prelude to a decade of fear, scientific discovery, and economic turmoil. The wake-up call came in May of 1980, just a week after the dramatic eruption of Mount St. Helens. A series of powerful earthquakes rocked the Mammoth Lakes area, a popular ski resort town nestled right on the edge of the caldera. 4 quakes, all registering around magnitude 6, struck in just 48 hours. Roads cracked, buildings were damaged, and the ground itself seemed to lurch and roll. For the residents and tourists, it was terrifying. The earth didn't just shake once. It kept going. This wasn't a normal earthquake sequence. It was a swarm, a relentless series of tremors that signaled something geological was happening on a massive scale. The scientific community, particularly the United States Geological Survey, or USGS, sprang into action. They knew Long Valley was a supervolcano, and these swarms were a classic sign of magma on the move. They descended on the area, deploying a sophisticated network of instruments. Seismometers to listen to the Earth's heartbeat, GPS stations to track the ground swelling, and gas sensors to sniff the air for volcanic fumes. What they found was alarming. The ground in the center of the caldera, an area known as the Resurgent Dome, was bulging upwards. By 1982, it had risen by nearly a foot. Magma was clearly intruding into the shallow crust. This put the USGS in an incredibly difficult position. They had a duty to warn the public of a potential volcanic hazard, but But they also knew that such a warning could cause panic and cripple the local economy, which depended entirely on tourism. In May 1982, after much debate, they issued a Notice of Potential Volcanic Hazard, the lowest level of alert. They communicated this to the public through the media, hoping to inform without inciting mass hysteria. The fallout was immediate and disastrous for Mammoth Lakes. The headlines were sensational. Supervolcano threatens California. Mammoth Lakes on brink of eruption. Tourists canceled their reservations in droves. The real estate market collapsed overnight. People who had invested their life savings into homes and businesses found themselves facing financial ruin. The town's economy, once booming, was devastated. There was immense anger directed at the USGS. Residents felt the scientists had cried wolf, destroying their livelihoods based on a threat that never materialized into an eruption. It was a painful lesson in the complex relationship between scientific warnings and public perception. The seismic swarms didn't stop. They continued throughout the 1980s and into the 1990s. The ground continued to swell. A particularly intense swarm in 1983 prompted further concern. The USGS even mapped out an escape route for the town, a plan that only heightened the sense of impending doom for many. One of the most striking signs of the magma's proximity to the surface appeared in 1989, near Horseshoe Lake, a popular recreational spot. A large area of trees began to die. Scientists discovered that they were being suffocated by huge quantities of carbon dioxide gas seeping up from the magma chamber below. The ground was literally gassing the forest to death. This was tangible, visible proof that the volcanic system was very much alive and dangerously active. The area had to be closed off to the public, a stark reminder of the invisible threat lurking just feet below. So, what exactly is Long Valley? Think of it as Yellowstone's slightly smaller but equally formidable California cousin. Both are calderas formed by massive, super eruptions in the distant past. The eruption that created Long Valley was one of the largest known on Earth, spewing out over 1,500 times more ash than the 1980 Mount St. Helens eruption. That ash, known as the Bishop Tuff, can be found as far away as Nebraska. It was a truly planet-altering event. The magma chamber beneath Long Valley is enormous, estimated to contain at least 2,400 cubic miles of molten and semi-molten rock. To put that in perspective, that's enough magma to fill the Grand Canyon several times over. While the intense activity of the 1980s has since calmed down, the caldera is by no means dormant. The ground continues to shift, the gases still seep, and the earthquakes, though less frequent, still occur. The events at Long Valley in the 1980s became a crucial case study for volcanologists worldwide. It highlighted the immense challenges of forecasting eruptions and the profound social and economic impacts of volcanic alerts. It forced scientists and public officials to rethink how they communicate risk. While the big one didn't happen, the decade-long unrest served as a powerful reminder that we live on a dynamic and powerful planet. The sleeping giant beneath California merely stirred in its sleep, but in doing so, it shook a community to its core and taught us a vital lesson about the immense forces that lie, waiting, just beneath our feet. Today, Mammoth Lakes has recovered, once again a thriving tourist destination. The USGS continues its vigilant watch, with monitoring technology far more advanced than what they had in the 80s. The story of Long Valley is a testament to both the terrifying power of nature and our enduring quest to understand and coexist with it. It's a geologic drama that is still unfolding chapter by chapter. Thanks for watching, and if you enjoyed this journey into the Earth's fiery heart, don't forget to like, subscribe, and hit that notification bell for more stories from our amazing planet. Both systems sit atop what geologists call hotspots, plumes of superheated rock rising from deep within the Earth's mantle, punching through the crust like blowtorches held against steel. Yellowstone's hotspot has been tracked backward through time, leaving a trail of ancient calderas across Idaho and into eastern Oregon, a breadcrumb path of destruction marking the North American plate's westward journey over this fixed point of heat. Long Valley's origins are more complex, possibly linked to the stretching and thinning of the crust in the Basin and Range Province, but the end result is eerily similar. Massive magma chambers, periodic supereruptions, and calderas that dwarf anything produced by conventional stratovolcanoes. The numbers tell the story of their kinship. Yellowstone's most recent supereruption, 640,000 years ago, ejected approximately 240 cubic miles of material. Long Valley's cataclysm, 760,000 years ago, released 150 cubic miles. These are not merely large eruptions. They represent a category unto themselves, events so energetic that they alter global climate, blanket continents in ash, and leave scars visible from space. Mount Vesuvius, which buried Pompeii and has terrorized Naples for millennia, is a firecracker by comparison. But size alone does not make them cousins. What truly links Yellowstone and Long Valley is their ongoing volatility, their refusal to settle into peaceful retirement. Both systems remain thermally active, heated from below by magma that never fully solidified, never retreated back into the mantle. At Yellowstone, this heat manifests in 10,000 geothermal features: geysers, hot springs, fumaroles, mud pots. The ground steams, the water boils. The earth literally hisses and spits, a constant reminder that beneath the beauty lies immense thermal energy seeking escape. Long Valley is more subtle in its expressions, but no less active. Hot Creek, a popular soaking spot for locals and tourists, runs warm even in winter, heated by water percolating through fractured rock and rising from the caldera's plumbing system. In the 1990s, areas around Mammoth Mountain began killing trees in vast swaths. Forest is dying not from disease or drought, but from carbon dioxide seeping up from below, suffocating roots, turning green slopes brown. Scientists measured CO2 concentrations in the soil high enough to be lethal to humans in enclosed spaces, a toxic breath from the magma chamber reminding everyone that the volcano was very much alive. Both calderas also share a pattern of episodic unrest, periods when seismic activity surges, when ground deformation accelerates, when scientists hold their collective breath wondering if this time the system will tip from restlessness into eruption. Yellowstone experiences earthquake swarms regularly, thousands of tremors clustered in time and space, often accompanied by measurable ground uplift or subsidence as magma and hydrothermal fluids shift position. These episodes can last months or years, raising public anxiety and scientific vigilance, then subside without producing any volcanic activity. Long Valley follows an almost identical pattern. The 1978 to 1982 crisis was not an isolated incident, but rather the most dramatic in a series of unrest episodes that continue to the present day. In 1989, another significant swarm shook the caldera. In 1997, seismicity spiked again beneath Mammoth Mountain. Each time, the USGS mobilized, analyzed data, assessed risk, and each time the system quieted without erupting, leaving scientists with more data but no definitive answers about what threshold, if any, would trigger the next eruption. This uncertainty is the curse and the challenge of supervolcano monitoring. Unlike well-behaved stratovolcanoes, such as Mount Rainier or Mount Shasta, which have regular magma plumbing and relatively predictable eruption, patterns calderas like Yellowstone and Long Valley are chaotic systems with multiple variables, complex feedback loops, and no clear correlation between unrest and eruption. Magma can intrude without erupting. Earthquakes can swarm without signaling imminent danger. The ground can rise for decades and then simply stop, pressure dissipating through pathways invisible to our instruments. Yet the comparison to Yellowstone also offers a framework for understanding risk. If Yellowstone were to experience a supereruption today, the consequences would be continental in scale. Ashfall rendering vast agricultural regions uninhabitable. Air traffic grounded across North America, climate disruption triggering global food shortages. Long Valley, while smaller, sits uncomfortably close to major population centers. Los Angeles is less than 300 miles south. The Central Valley, which feeds much of America, lies directly downwind. An eruption, even a fraction of the caldera's historic capacity, would be a national catastrophe. And so scientists watch both systems with equal intensity, knowing they are monitoring not just volcanoes but geological time bombs whose fuses are invisible and whose detonation, if it comes, will reshape the continent. Reading The Restless Giant by the mid-1980s, Long Valley had become a proving ground for volcanic monitoring technology, a place where theory met reality and where scientists learned, sometimes painfully, the limits of their ability to predict what the Earth would do next. The caldera was no longer just a geological curiosity. It was a laboratory with 8,000 people living inside it, a high-stakes experiment and risk assessment where mistakes could cost lives or livelihoods. The seismic network installed throughout the caldera recorded every tremor, every tiny fracture. in the rock building a three-dimensional map of earthquake hypocenters that revealed where stress was concentrating, where magma might be moving, where the crust was being pulled apart by forces from below. What emerged from this data was a picture of extraordinary complexity. The earthquakes were not random. They clustered in specific zones, particularly beneath the resurgent dome, a raised area in the south-central part of the caldera, where the ground had been uplifted more than half a mile since the original collapse 760,000 years ago. This dome is not merely a feature of past geology. It is active, growing, being pushed upward by magma intrusion that continues in the present day. The earthquakes beneath it told a story of rock being stretched to its breaking point, of molten material forcing its way into cracks and fissures, seeking pathways toward the surface. Some earthquakes occurred at depths of 10 to 15 miles, deep in the crust where temperatures are high enough to keep rock partially molten. Others occurred much shallower, only a mile or two down, close enough that scientists worried about the possibility of a phreatic eruption, a steam-driven blast caused when rising magma contacts groundwater. But earthquakes alone could not tell the full story. Ground deformation measurements provided another critical piece of the puzzle. Using a technique called leveling, scientists repeatedly surveyed precise elevation points throughout the caldera, comparing measurements year after year to detect vertical movement. What they discovered was unsettling. The center of the caldera had risen more than 30 inches between 1975 and 1983, an extraordinary rate of uplift that indicated substantial magma accumulation at depth. Later, as technology advanced, GPS stations and satellite-based interferometry allowed for continuous, real-time monitoring of ground deformation with millimeter precision. These tools revealed that the uplift was not constant but episodic, accelerating during earthquake swarms and sometimes reversing slightly during quiet periods, as if the caldera were breathing, inhaling magma and pressure, then exhaling just enough to release tension without exploding. Gas monitoring added yet another dimension to the surveillance effort. Volcanoes emit gases long before they erupt, changes in chemistry and volume that can signal magma ascent or increased hydrothermal activity. Scientists sampled fumaroles and hot springs throughout Long Valley, analyzing ratios of carbon dioxide, sulfur dioxide, helium isotopes, and other volatile compounds. Elevated CO2 levels, particularly around Mammoth Mountain, confirmed that magmatic gases were reaching the surface, diffusing through fractured rock, finding release in areas where the overlying seal had weakened. In 2006, the discovery of a massive CO2 emission zone on Mammoth Mountain's flanks prompted the U.S. Forest Service to close certain areas to the public after several ski patrol members experienced near asphyxiation in a snow-covered cabin where gas had accumulated. The invisible threat was in some ways more terrifying than earthquakes or ground cracks. You could not see it, could not smell it in concentrations below lethal levels, could only trust instruments and warning signs to keep you safe. Temperature monitoring in shallow boreholes and thermal imaging from aircraft revealed heat anomalies that mapped the pathways of hydrothermal circulation, where water heated by magma at depth rose convectively and released heat near the surface. Some areas showed temperature increases over time, suggesting that the hydrothermal system was becoming more vigorous, driven by fresh heat input from below. All of this data flowed into the USGS Monitoring Center, where scientists worked to synthesize disparate signals into a coherent assessment of volcanic threat. But integration proved maddeningly difficult. Sometimes earthquakes increased while deformation slowed. Other times gas emissions spiked without corresponding seismic activity. The caldera refused to behave predictably, refused to follow the neat patterns that might allow for confident forecasting. The scientific community debated what threshold would constitute a genuine eruption precursor. How much uplift was too much? How many earthquakes per day indicated imminent danger? What gas ratios signaled shallow magma versus merely vigorous hydrothermal activity? These questions had no clear answers because Long Valley, like all large calderas, had no modern eruption in the instrumental record to serve as a template. Scientists were forced to rely on data from other volcanoes, from smaller systems with different plumbing, knowing that the comparison might not hold. And so the monitoring continued year after year, an unblinking technological vigil over a geological giant that might sleep for another 1,000 years or might awaken tomorrow. The instruments recorded every heartbeat, every breath, building an archive of data unprecedented in volcanic science, waiting for the day when pattern would become prediction, when restlessness would finally tip into action, and when all the watching would either justify itself with timely warning or reveal itself as inadequate against the fury of the earth.
By the mid-1980s, Long Valley had become a proving ground for volcanic monitoring technology, a place where theory met reality and where scientists learned, sometimes painfully, the limits of their ability to predict what the Earth would do next. The caldera was no longer just a geological curiosity. It was a laboratory with 8,000 people living inside it, a high-stakes experiment in risk assessment where mistakes could cost lives or livelihoods. The seismic network installed throughout the caldera recorded every tremor, every tiny fracture in the rock, building a three-dimensional map of earthquake hypocenters that revealed where stress was concentrating, where magma might be moving, where the crust was being pulled apart by forces from below. What emerged from this data was a picture of extraordinary complexity. The earthquakes were not random. They clustered in specific zones, particularly beneath the resurgent dome, a raised area in the south-central part of the caldera where the ground had been uplifted more than half a mile since the original collapse 760,000 years ago. This dome is not merely a feature of past geology. It is active, growing, being pushed upward by magma intrusion that continues in the present day. The earthquakes beneath it told a story of rock being stretched to its breaking point, of molten material forcing its way into cracks and fissures, seeking pathways toward the surface. Some earthquakes occurred at depths of 10 to 15 miles, deep in the crust where temperatures are high enough to keep rock partially molten. Others occurred much shallower, only a mile or two down, close enough that scientists worried about the possibility of a phreatic eruption, a steam-driven blast caused when rising magma contacts groundwater. But earthquakes alone could not tell the full story. Ground deformation measurements provided another critical piece of the puzzle. Using a technique called leveling, scientists repeatedly surveyed precise elevation points throughout the caldera, comparing measurements year after year to detect vertical movement. What they discovered was unsettling. The center of the caldera had risen more than 30 inches. Between 1975 and 1983, an extraordinary rate of uplift that indicated substantial magma accumulation at depth. Later, as technology advanced, GPS stations and satellite-based interferometry allowed for continuous, real-time monitoring of ground deformation with millimeter precision. These tools revealed that the uplift was not constant but episodic, accelerating during earthquake swarms and sometimes reversing slightly during quiet periods, as if the caldera were breathing, inhaling magma and pressure, then exhaling just enough to release tension without exploding. Gas monitoring added yet another dimension to the surveillance effort. Volcanoes emit gases long before they erupt. Changes in chemistry and volume that can signal magma ascent or increased hydrothermal activity. Scientists sampled fumaroles and hot springs throughout Long Valley, analyzing ratios of carbon dioxide, sulfur dioxide, helium isotopes, and other volatile compounds. Elevated CO2 levels, particularly round Mammoth Mountain, confirmed that magmatic gases were reaching the surface, diffusing through fractured rock, finding release in areas where the overlying seal had weakened. In 2006, the discovery of a massive CO2 emission zone on Mammoth Mountain's flanks prompted the U.S. Forest Service to close certain areas to the public after several ski patrol members experienced near asphyxiation in a snow-covered cabin where gas had accumulated. The invisible threat was in some ways more terrifying than earthquakes or ground cracks. You could not see it, could not smell it in concentrations below lethal levels, could only trust instruments and warning signs to keep you safe. Temperature monitoring in shallow boreholes and thermal imaging from aircraft revealed heat anomalies that mapped the pathways of hydrothermal circulation. where water heated by magma at depth rose convectively and released heat near the surface. Some areas showed temperature increases over time, suggesting that the hydrothermal system was becoming more vigorous, driven by fresh heat input from below. All of this data flowed into the USGS Monitoring Center, where scientists worked to synthesize disparate signals into a coherent assessment of volcanic threat. But integration proved maddeningly difficult. Sometimes earthquakes increased while deformation slowed. Other times gas emissions spiked without corresponding seismic activity. The caldera refused to behave predictably, refused to follow the neat patterns that might allow for confident forecasting. The scientific community debated what threshold would constitute a genuine eruption precursor. How much uplift was too much? How many earthquakes per day indicated imminent danger? What gas ratios signaled shallow magma versus merely vigorous hydrothermal activity? These questions had no clear answers because Long Valley, like all large calderas, had no modern eruption in the instrumental record to serve as a template. Scientists were forced to rely on data from other volcanoes, from smaller systems with different plumbing, knowing that the comparison might not hold, and so the monitoring continued. Year after year, an unblinking technological vigil over a geological giant that might sleep for another 1,000 years or might awaken tomorrow. The instruments recorded every heartbeat, every breath, building an archive of data unprecedented in volcanic science, waiting for the day when pattern would become prediction, when restlessness would finally tip into action, and when all the watching would either justify itself with timely warning or reveal itself as inadequate against the fury of the earth.
The paradox at the heart of volcanic monitoring became painfully clear as the years passed and Long Valley refused to erupt. Every instrument told scientists that the caldera was active, that magma was present at shallow depths, that the conditions existed for volcanic activity. Yet eruption never came. The gap between activity and eruption, between unrest and catastrophe, proved to be a chasm that science could describe but not bridge with prediction. David Hill, the USGS scientist who became the public face of Long Valley monitoring, found himself in an unenviable position. He understood the data better than almost anyone, could read the seismograms and deformation graphs with the fluency of a native language. Yet when reporters or town officials asked the only question that truly mattered, will it erupt? He could offer only probabilities, ranges, conditional statements hedged with caveats. The honest answer was that nobody knew, and honesty, in a community desperate for certainty, often sounded like evasion. The challenge was not lack of data, but rather the complexity of the system itself. Magma chambers are not simple balloons that inflate until they pop. They are dynamic environments where molten rock, crystals, and gas exist in constantly shifting equilibrium, influenced by temperature, pressure, the strength of surrounding rock, the presence of groundwater, and a dozen other variables that interact in non-linear ways. A caldera can show every sign of impending eruption and then stabilize as magma solidifies at depth or finds release through pathways that never reach the surface. Historical analogs offered little comfort. Rabaul caldera in Papua New Guinea experienced intense seismic swarms and ground deformation for more than a decade before finally erupting in 1994, but the eruption, when it came, was far smaller than feared. Campi Flegrei near Naples has been rising and falling for centuries, causing periodic evacuations and panic, yet has not erupted since 1538. Each restless caldera follows its own timeline, obeys its own internal logic, making prediction a matter of informed speculation rather than scientific certainty. The USGS developed a color-coded alert system to communicate volcanic threat levels to the public, a scheme borrowed from aviation weather warnings. Green meant normal background activity. Yellow indicated elevated unrest above baseline. Orange signaled heightened unrest with increased potential for eruption. Red meant eruption was imminent or underway. Long Valley has oscillated between green and yellow for decades, occasionally spiking to orange during particularly intense earthquake swarms, but never reaching red. These designations meant to clarify often confused. What did yellow mean in practical terms? Should residents leave? Should they cancel vacation plans? The alert levels described scientific assessment, but could not dictate personal risk tolerance. Some families moved away permanently after the 1982 notice, unwilling to live with uncertainty. Others stayed, decided that the economic opportunities or quality of life in Mammoth Lakes outweighed the volcanic risk, made peace with living atop a restless giant. The economic tension never fully resolved. Every time the USGS raised the alert level, even modestly, tourism took a hit. Hotel owners watched reservations cancel. Ski resorts saw season pass sales decline. Real estate agents struggled to sell properties in a town where prospective buyers Googled Long Valley Volcano and found alarming articles about supervolcanic potential. The resentment towards scientists who had made the threat public simmered beneath civic politeness, surfacing in heated town hall meetings where business owners demanded to know why the USGS kept scaring people away with warnings that never materialized into actual eruptions. Yet the scientists could not, in good conscience, remain silent. The magma was real, the earthquakes were real. The ground deformation was real. To downplay these facts simply to protect tourism revenue would be a betrayal of public safety and scientific integrity. The ethical obligation was to inform, to explain risk as clearly as possible, and to let individuals and communities make their own decisions about how to respond. This tension between scientific responsibility and economic impact is not unique to Long Valley. It plays out at every monitored volcano where people have chosen to live in the shadow of potential disaster. Vesuvius looms over 3 million people in the Naples metro area. Mount Rainier towers above Tacoma and Seattle. The Cascades volcanoes watch over cities and towns throughout the Pacific Northwest. In each case, scientists must balance the duty to warn against the knowledge that false alarms erode public trust, and that crying wolf, even with the best intentions, can make communities deaf to future warnings. Long Valley became a case study in this dilemma, a place where the science was excellent, the monitoring state-of-the-art, the communication thoughtful and transparent, yet the outcome remained unsatisfying because the fundamental question, when will it erupt if ever, had no answer. The caldera hummed with activity, breathed with pressure changes, trembled with earthquakes, but kept its ultimate intentions hidden beneath miles of rock. By the early 2000s, a kind of equilibrium had settled over Mammoth Lakes. The monitoring continued, the alert levels shifted periodically. But the community had learned to live with uncertainty, had integrated volcanic risk into the background calculation of daily life, much as Californians accept earthquake risk or Floridians accept hurricanes. It was the price of living in a beautiful, geologically active landscape, a bargain struck with the earth that could be revoked at any moment, but for now held steady.
For the residents and business owners of Mammoth Lakes, the CO2 threat added another layer of anxiety to an already complex relationship with the volcano. It was no longer sufficient to monitor earthquakes and ground deformation. Now they had to consider invisible gases, to trust that sensors and warning systems would protect visitors from a hazard that offered no sensory warning of its presence. The mountain that sustained their economy also harbored a hidden danger that could kill without announcement, a reminder that volcanic risk takes many forms and that sometimes the greatest threat comes not from what explodes but from what seeps silently from the depths. As the calendar turned from the 20th century into the 21st, Long Valley Caldera settled into a pattern that defied both pessimistic predictions and optimistic hopes. The system remained active, unquestionably so, yet refused to escalate toward the catastrophic eruption that worst-case scenarios had envisioned. Scientists accumulated decades of high-quality data, built sophisticated computer models of magma chamber dynamics, published dozens of peer-reviewed papers, and still could not answer the question that haunted every resident of Mammoth Lakes: will it erupt in our lifetime? The geological evidence suggested that Long Valley's eruptive history since the caldera-forming event 760,000 years ago has been episodic and varied. The caldera has produced numerous smaller eruptions over the millennia, building the resurgent dome through repeated injections of viscous, rhyolitic magma, creating volcanic vents and lava domes scattered across the landscape. The most recent confirmed eruption occurred approximately 600 years ago, a modest event by volcanic standards but proof that the system retains the capacity for surface activity. What scientists debate is not whether Long Valley can erupt again. It almost certainly can, but rather what form that eruption might take and when it might occur. The nightmare scenario, the one that keeps volcanologists awake at night, is a repeat of the caldera-forming supereruption. The magma chamber appears to have partially refilled over the past 760,000 years, accumulating fresh molten material injected from the mantle below. Seismic imaging reveals a substantial body of partially molten rock at depths between 4 and 6 miles, a reservoir large enough to fuel a major eruption if the conditions aligned. But supereruptions are rare precisely because the conditions required for them are extraordinarily specific. The magma must reach a critical volume and gas content. The roof rock must be sufficiently weakened to fail catastrophically rather than leak pressure gradually. The system must accumulate energy faster than it can dissipate through earthquakes, ground deformation, and gas emissions. Most restless calderas never cross these thresholds. They inflate, they earthquake, they breathe gas, and then they stabilize, the energy dissipating through pathways that prevent catastrophic release. More likely, scientists believe, is a smaller eruption, perhaps similar to the events that built Mammoth Mountain or created the Inyo craters just north of the Caldera. These eruptions, while serious, are manageable disasters rather than civilization-ending catastrophes. They would produce lava flows, pyroclastic surges, ashfall measured in inches rather than feet, hazards that could be survived with preparation and timely evacuation. The challenge is that even a small eruption from Long Valley would devastate Mammoth Lakes, varying infrastructure, contaminating water supplies, rendering the town uninhabitable for years or decades. The monitoring data from recent decades shows a system in flux, but not necessarily in escalation. Ground deformation rates, after the dramatic uplift of the late 1970s and early 1980s, have slowed considerably. Some areas of the caldera have even subsided slightly, suggesting that pressure is being released through crustal adjustments rather than accumulating toward eruption. Earthquake swarms still occur, sometimes intensely, but they no longer provoke the same level of alarm they did in the 1980s. The community has developed a tolerance for background such a learned ability to distinguish between routine unrest and genuine emergency. Yet complacency is dangerous. Volcanoes are patient. They operate on timescales that dwarf human planning horizons. A caldera can rest quietly for centuries and then erupt with little warning. Kilauea, in Hawaii, one of the world's most active volcanoes, lulled observers into expecting effusive lava flows, and then in 2018 produced explosive eruptions in a summit collapse that surprised even veteran Long Valley could do the same, shifting from its current pattern of chronic low-level unrest into rapid escalation that compresses weeks of warning signs into days or hours. The USGS has developed contingency plans for various eruption scenarios, working with local emergency managers to identify evacuation routes, establish communication protocols, and pre-position resources. But planning is only valuable if warning time is adequate. Some volcanic eruptions announce themselves weeks in advance, with unmistakable precursors. Dramatic increases in accelerating ground deformation, changes in gas composition and flux that clearly indicate rising magma. Others give hours or minutes, catching communities off guard despite sophisticated monitoring. The social contract between scientists and the public at Long Valley rests on an implicit promise that monitoring will provide enough warning for evacuation, that the instruments will detect escalation before it becomes disaster. But that promise, though made in good faith, cannot be guaranteed. Volcanoes do not always cooperate. They do not always follow the patterns established by previous eruptions or by analogs elsewhere. The possibility exists, however remote, that Long Valley could transition from background unrest to eruption faster than monitoring could track or authorities could respond.
This uncertainty is the burden that the people of Mammoth Lakes carry, a weight made heavier by its invisibility. Tourists arrive, ski the slopes, soak in the hot springs, and leave without contemplating the fire below. But those who live there year-round, who have raised children in the shadow of the caldera, who have watched property values fluctuate with every USGS alert level change, cannot afford such ignorance. They have made peace with risk, accepted that their home is beautiful precisely because it is geologically alive, and chosen to trust that when the mountain finally decides to speak, it will give them enough time to listen and to run. Vigilance without end. The California Volcano Observatory, established by the USGS in 2012, represents the institutional commitment to perpetual watchfulness over Long Valley and the other volcanic systems that dot the state's landscape. It is not a single building, but rather a network of scientists, instruments, and communication protocols designed to ensure that no significant change in volcanic activity goes unnoticed. At Long Valley, this vigilance translates into one of the most comprehensive monitoring systems ever deployed at a volcanic field. More than 40 seismic stations encircle and penetrate the caldera, their sensors buried in shallow boreholes to minimize noise from wind and human activity. These instruments detect earthquakes too small for humans to feel, tremors with magnitudes below 1, microfractures in the rock that reveal stress accumulation and magma movement. The data streams continuously to computers that analyze waveforms in real time, automatically locating earthquake hypocenters, calculating magnitudes and flagging unusual patterns that might indicate escalating unrest. GPS stations fixed to bedrock throughout the region measure ground position with millimeter precision, tracking the slow dance of deformation as the caldera breathes. Unlike the labor-intensive leveling surveys of earlier decades, which required field crews to physically visit benchmarks and measure elevations, GPS operates continuously and autonomously, transmitting data via satellite to monitoring centers where algorithms detect deviations from baseline. When the ground rises or subsides, when horizontal strain accumulates along fault zones, the GPS network reveals these changes in near real time. Satellite-based interferometric synthetic aperture radar, known as INSAR, provides another layer of surveillance. Satellites orbiting hundreds of miles above the Earth emit radar pulses that bounce off the ground and return to the spacecraft. By comparing radar images taken weeks or months apart, scientists can create detailed maps of ground deformation across the entire caldera, detecting changes as small as a centimeter over areas spanning hundreds of square miles. INSAR reveals deformation in remote areas where installing ground-based instruments would be impractical, filling gaps in the monitoring network and providing a comprehensive view of how the entire caldera is moving. Gas monitoring has also evolved beyond periodic sampling trips. Permanent stations now measure carbon dioxide flux continuously at multiple sites around Mammoth Mountain and within the caldera, tracking not just concentration but also the rate at which gas is escaping from the Earth. Spectrometers analyze the chemical and isotopic composition of gases, distinguishing between shallow hydrothermal sources and deep magmatic contributions. When magma rises, the signature changes: higher temperatures, different gas ratios, isotopes that fingerprint the source as freshly ascended from the mantle. Web cameras positioned at strategic locations provide visual monitoring, capturing images every few minutes that can reveal changes invisible to seismometers and GPS. New fumaroles steaming on previously quiet slopes, ground cracks opening lakes changing color due to altered chemistry. These cameras also serve a public communication function, allowing anyone with internet access to view the caldera in real time, demystifying the monitoring process and providing transparency that builds trust between scientists and the community. All of this data converges at the California Volcano Observatory's Operations Center, where scientists maintain a continuous watch, reviewing incoming data streams, investigating anomalies, consulting with colleagues when patterns deviate from expectations. During periods of heightened unrest, the watch intensifies, with staff working extended shifts, briefing emergency managers, preparing information releases for the media and public. The goal is never to be surprised, to catch escalation early enough that warnings can be issued with confidence and time. But technology alone cannot eliminate uncertainty. The instruments can tell scientists what is happening: magma is moving, pressure is building, gas is escaping, but not what will happen. The leap from observation to prediction remains fraught with difficulty. Every earthquake swarm raises the same question: is this the beginning of an eruptive sequence, or just another episode of unrest that will subside without incident? The data provides clues, probabilities, but rarely certainty. The challenge is compounded by the fact that Long Valley has no modern baseline. Unlike Mount St. Helens, which scientists studied intensively before, during, and after its 1980 eruption, providing a detailed record of precursory signals and eruptive behavior, Long Valley has not erupted in the instrumental era. Scientists cannot point to a previous event and say, this is what it looked like last time. They must infer from analogs, from other calderas, from theoretical models, knowing that when and if Long Valley erupts, it may not follow the script written by other volcanoes. The monitoring network also faces practical challenges. Instruments fail, batteries die, sensors drift out of calibration, wildlife damages cables. Winter storms bury equipment under snowdrifts. Maintaining continuous, high-quality data streams from dozens of remote stations scattered across rugged terrain requires constant attention, regular maintenance visits, and backup systems to ensure that no critical gap in coverage occurs at the worst possible moment. Despite these challenges, the monitoring network at Long Valley represents one of the success stories of modern volcanology. The data archive now spans more than 4 decades, a record of unparalleled length and quality that has advanced scientific understanding of caldera systems worldwide. Researchers studying restless calderas in Japan, New Zealand, Italy, and elsewhere regularly consult Long Valley data, looking for patterns and insights that might apply to their own monitored systems. And the vigil continues year after year, through periods of quiet and periods of unrest, through budget cycles and changes in personnel, a commitment to watchfulness that transcends individual careers and administrations. The instruments listen. The satellites watch, the scientists analyze. And somewhere below, in the darkness miles beneath the surface, the magma waits, patient and inscrutable, keeping its own counsel about what the future holds. There is a kind of wisdom that emerges from living beside forces you cannot control, an acceptance that borders on fatalism but is really something more profound. An acknowledgement that safety is always provisional, that the ground beneath your feet is not as stable as it appears, that the earth is alive in ways that dwarf human concerns and human timelines. The people of Mammoth Lakes have learned this wisdom not from books but from experience, from feeling their houses shake at 3 a.m, from watching scientists install yet another monitoring station, from the casual way locals discuss earthquake swarms over coffee as if commenting on the weather. This is not resignation. It is adaptation. Humans have always lived in the shadow of volcanoes, drawn to the fertile soils they create, the geothermal energy they provide, the dramatic beauty of landscapes shaped by fire. From the slopes of Mount Etna to the flanks of Mount Fuji, from the shores of Lake Taupo to the highlands of Guatemala, millions of people worldwide make their homes on or near active volcanoes, calculating that the benefits outweigh the risks, or simply accepting that risk is the price of living where they choose to live. Long Valley is no different in this regard, though its risk profile is more complex than most. A stratovolcano like Mount Fuji presents a relatively straightforward hazard: lava flows, pyroclastic surges, ashfall, lahars. The dangers are directional, flowing downslope, allowing for evacuation planning based on topography and prevailing winds. A caldera like Long Valley presents hazards that are more diffuse and harder to predict. An eruption could occur anywhere within the 20-mile-long depression, from vents that have no historical precedent, along fault lines that have shown no recent activity. The ashfall could blanket the entire region. Gas emissions could make large areas uninhabitable without fire ever reaching the surface. Yet the community persists, grows even. Mammoth Lakes has evolved from a struggling mining town to a thriving resort community with a year-round population, approaching 8,000 and seasonal visitation in the hundreds of thousands. The economy depends almost entirely on tourism, skiing in winter, mountain biking and hiking in summer, fishing and hot springs year-round. People come precisely because the landscape is dramatic, because the mountains are young and sharp, because the hot creeks and geothermal features signal a living earth rather than a dead one. The paradox is that the same geological forces that create the hazard also create the attraction. Without the volcanic activity, there would be no Mammoth Mountain, no hot springs, no dramatic scenery carved by ancient eruptions and sculpted by glaciers that formed in the cool periods following massive ash injections into the atmosphere. The beauty and the danger are inseparable, two faces of the same geological reality. Education has become part of the community's adaptation strategy. Schools teach children about volcanoes, not to frighten them but to instill respect and preparedness. Emergency drills include volcanic scenarios alongside earthquake and wildfire protocols. The town maintains evacuation routes, regularly reviews emergency plans with county and federal agencies, and ensures that communication systems can function even if power fails. There is an understanding, unspoken but pervasive, that ignorance is a luxury they cannot afford. The scientific community, for its part, has learned its own lessons from 4 decades of monitoring Long Valley. The early missteps, the 1982 hazard notice that devastated tourism without producing an eruption, taught the importance of clear communication and careful calibration of warnings. The USGS now works closely with local officials before issuing alert level changes, providing context, explaining uncertainties, ensuring that warnings are neither alarmist nor complacent. The relationship between scientists and community, once strained by mutual suspicion, has matured into something resembling partnership, built on transparency and repeated interactions over many years. But the fundamental uncertainty remains. Long Valley is a puzzle with missing pieces, a system whose behavior can be described but not predicted with confidence. The magma chamber exists, indisputably. The potential for eruption is real. The monitoring network will detect escalation if it occurs. But whether that escalation will happen next year, next century, or not for 10,000 years, no instrument can reveal. This uncertainty is perhaps the caldera's greatest legacy, a lesson in humility for a civilization accustomed to mastering its environment through technology and understanding. We can split atoms, sequence genomes, send probes to the edge of the solar system. Yet we cannot say with certainty whether a restless volcano will erupt. The Earth keeps secrets that satellites cannot penetrate, that seismometers cannot decode, that computer models cannot predict. And so the watching continues, the vigilance without end, a commitment to preparedness in the face of unknowable odds. The instruments record every tremor. The scientists analyze every signal. The community goes about its daily life, skiing the mountain, raising families, building businesses, always aware, but not paralyzed by the knowledge that beneath the beauty lies power enough to reshape the continent. In the end, Long Valley teaches what all volcanoes teach, that we are guests on a dynamic planet, that the ground we build upon is temporary and geological, time that nature operates on scales and timelines indifferent to human habitation. We can monitor, prepare, warn, evacuate, but we cannot control. We can only watch, wonder, and make our peace with forces older and greater than ourselves, forces that were here long before us and will endure long after we are gone. The fury of the earth is patient, ancient, and ultimately inscrutable. And perhaps that is exactly as it should be. The fury of the earth is patient, ancient, and ultimately inscrutable. And perhaps that is exactly as it should be. But you don't have to face these mysteries alone. Here at Fury of the Earth, we're committed to bringing you the stories that matter, the science that saves lives, the truth about the planet we call home. If this documentary moved you, if it made you think, if it gave you a new respect for the forces beneath our feet, then join our community. Subscribe, hit the bell icon. Leave a comment telling us what you thought or what volcano you want us to explore next. Because the Earth will never stop moving, and neither will we. Until next time, stay curious, stay safe, and remember, the ground you stand on has a story to tell.